Today's outcome is to continue working on your equilibrium practice problems. For the opening question, take a moment to tell another student at your table one tip that will help them solve equilibrium problems. Before you start working on your problems today, I want to show you an example of how to do one of the ones on your sheet. I'm going to go slowly so you can think about the answers yourself before I say the next step. Match the picture on your paper so you can read the problem. There are two blocks. One is going down an incline and one is going straight down on a rope. Since they're both connected to the same rope, the tension on each of the blocks will be the same. The first thing we have to do is draw a free body diagram. The forces on the hanging block will be force of gravity and force of tension. I'm going to get a narrower pen. The forces on the sliding block are, now pay attention to the angle that I draw this vector. The force of gravity, still straight down, even though it's on an incline. Normal force. Tension. And then the block is trying to slide this way because it's being pulled by the hanging block, so the force of friction will be in the opposite direction, right here. To set up my equations, this is a 15 Newton block here, so the force of gravity is equal to 15. The first question asks, what is the weight of this block so that this block will not slide? That means acceleration in the x direction will be equal to 0, and acceleration in the y direction will be equal to 0. Let's set up our force equation for the x direction. Now, if I use y as the vertical, I'm going to have 3 vector triangles. But if I stand on the incline like this, these forces are all horizontal. This one is vertical, and our force of gravity is at an angle. And this will be FGX, and this side will be FGY. So the forces in the x direction will be positive FF, because it's to the right, minus FT plus FGX. And all of that will equal MAX. In the y direction, we have positive Fn going up minus FGY equal to MAY. Now let's put in the information that we know. FF is equal to mu Fn minus Ft plus, now FG is 15, so the hypotenuse of this triangle is 15. The angle at the top is 31. So, to find FGX, that's opposite to 31, sine 31 equals FGX divided by 15, or 15 sine 31 equals FGX. So 15 sine 31 is 7.7. Now I go up to the equation and I put 7.7 in here. The mass of the block will be 15 newtons divided by 9.8, because mass is in kilograms, times the acceleration, which is 0. So if I simplify one more line, I know my coefficient is 0.7, so I'll put that in here. Fn minus Ft plus 7.7 equals 0. This equation, Fn minus Fgy, will be cosine of 31 equals Fgy divided by 15. Multiply both sides by 15. 15 cosine 31 equals Fgy. And that is equal to 12.86. Call it 12.9 equals FGY. 12.9 equals the mass, which is 15 divided by 9.8, times acceleration, which is 0, because we want them to be balanced. So this is 0, so I get Fn equals 12.9. And 7 times 12.9 minus Ft equals negative 7.7. Negative Ft equals negative 7.7 minus 0.7 times 12.9. Move the screen down so I have a little more space here. Put it right here. Ft equals 16.73. Now that was not what the problem asked me for, so I'm not finished yet. It said, what mass does this block have to be so that this one will not slide? So I have the force of tension. Now I'm going to change colors. And now I'm going to calculate for this block, knowing my Ft, what the Fg has to be. I think most of you already know what that answer is going to be. I'm going to use the y direction. Equals MAY equals Ft is positive minus Fg, because it's going down. Mass we don't know for the blue block, times acceleration is 0 because it's not sliding. Ft is 116.73 minus Fg. This is 0, so I'm going to move this over to this side. So force of gravity equals 16.73 newtons. And that is the weight, because newtons is weight, of the hanging block that will hold the sliding block in place. That is not the answer to the entire problem. There's a second part to this. If you read your question, it says, how much mass must the hanging block have to allow the block on the incline to lower at a constant acceleration of 2 meters per second squared? So since we just talked about this problem, you might want to do the second half of this one right away before we move on to the next one. Let me move this up a little bit in case you want to pause it on the screen. You can see the entire problem worked out all at once, everything except the last words. By the end of the class period, I want you also to complete, in addition to working these problems, a closing question, which I had conveniently typed for you here. For closing today, I want you to explain how to solve one of these equilibrium problems. Use an example in your response. Any of those problems, you can do one of the ones we did together, or one of the ones you did on your own. Make sure you actually write it out in correct grammar and write it for an audience that would be a student who has never seen one of these problems. So if you're going to use SOHCAHTOA, you need to explain how you did that. If you're going to label your forces, you need to explain that the forces, when you draw them, could be gravity, tension, friction, or a force of one thing on another, like a force of someone pulling or pushing, or the force of a foot on a floor, something like that. So make sure you have a nice, careful, detailed response. You may want to start writing it early enough so that you can do a draft and then revise it to get a final copy. Make sure you hand that into the substitute before the end of class. I'll leave it on the screen at the end in case you need to see that as an example again. Good luck, and I know you'll work hard today.